So let's see the part 2 topics from unit 4. So under part 2 we have preemptive real-time operating systems, priority based scheduling and inter-process communications. Okay. So part 1 we have already discussed about multiple tasks and processes, multi-rate systems. So under the part 2 we have the first topic as preemptive real-time operating systems. So what do you mean by preemptive real-time operating systems? A preemptive real-time operating systems, it is used to solve the fundamental problems of cooperative multitasking systems. You all know what is multitasking, right? So when when two or many tasks are done in a single interval of time, that we called it as multitasking. So in the system, multitasking is possible. So at the same time, the multitasking will also create some problems or issues. Okay, so it executes processes based upon timing requirements, okay, provided by the system designer. So this is already pre-programmed by the system designer, and the system designer will be giving or setting some sort of delay or timing to each and every process. Okay, so based upon the timing, the tasking can be performed with the help of preemptive real-time operating system. Okay, so this preemptive real-time operating system is most reliable way to meet timing requirements accurately, and it is used to priority to control what process runs at any given time. So there are two things. It is fixing the time and also it is giving the priority to what process is running at any given time. So there are two basic concepts under preemptive scheduling algorithm. The first concept is that it is going to be an alternative to the C function to control the execution. It is one of the way to control the execution. The second is it is going to fit some priority, to introduce priority based scheduling as a way for the programmer to control the order in which the process runs. Okay, so the first thing is it is going to be an alternative of C function, that is a way to control the execution. Second, it is going to introduce the priority. Okay, so now let us assume a new routine, okay, that allows to jump from one subroutine to another at any point in the program. So what do you mean by routines and subroutines? Routines, it may be a set of tasks, and subroutines, it depends upon the main routine. Okay, so let us allow the new routine that allow us to jump from one subroutine to another. So this is possible by having only one main routine and jumping from one subroutine to another subroutine. It is possible in a program. Okay, so that together with the timer will to move between the functions whenever necessary based upon the system's timing constraints. So now what we are going to do is we are going to jump from one subroutine to another. Okay, so now you see the figure shown is the example of preemptive execution of an operating system. The objective is to share the CPU across two processes. Okay, so we are going to use two processes, but the two processes, they are going to use the same CPU. Okay, you see the same figure is copied here. So in this diagram you can see the system which is called as kernel. Okay, so this kernel is a part of the operating system that determines what processor is running. The kernel is activated periodically by the timer. Okay, so you can see after some instant of time the kernel is activated. Okay, so when the task 1 has completed, it returns to the timer, and then the timer will be activating the kernel. After the kernel job is completed, it is given to the task 2. Okay, so now the length of the timer period is known as quantum. Okay, so this is called as a quantum because it is the smallest increment in which CPU activity can be controlled. Okay, that is what happens after the completion of the task 1. It is the control is given to the timer, that is time quantum. Okay, so increment in which the CPU activity can be controlled. Okay, kernel determines what processor will run next. Okay, so this kernel is going to determine what processor is going to be running at each and every phases. On the next timer interrupt, the kernel may pick the same process or another process to run. Okay, so now task 1 is completed and it is interrupted by the timer. Okay, so after the timer interrupt, after the quantum time, what happens? It is given to the kernel. Kernel is going to be the operating system. Okay, so now it determines, okay, it should be given to the operating system should be shared to the CPU, should be shared to the task 2. Okay, it may be based upon the priority. Maybe the task 2 will be having the high priority now, so it is given to the task 2. Okay, after that what happens? Again, after completing the task 2 or after a set of delay, it is given to the timer, and then what happens? The timer again will give the control to the kernel, and the kernel will decide what priority is going to happen, whether it may be a task 1 or task 2, or it may be a multitasking system. Okay, so the kernel may pick the same process or another process to run based upon the priority. So now, under the preemptive scheduling algorithm, we have the next topic as context switching mechanism. Okay, the context switching mechanism is a process that can be switched by other process by using the assembly language. Okay, the timer interrupt causes to control to change from the currently executing process to the kernel. Okay, assembly language can be used to save and restore registers. So this context switching mechanism is using the language which is called as assembly language. Why they are going for the assembly language is like the kernel, what does it do? The kernel, whenever the timer interrupt causes, the control is given to the kernel. The kernel is the one which decides what kind of task is going to be done. Okay, so at each and every task, on the incompletion of each and every task, the task should be stored in some registers, right? So like how the program counter does, right? So the program counter, what is the use of the program counter? It stores the address of the current instruction to be executed. Okay, after the interrupt, after answering to the priority, what happens? It restores the registers. So for that purpose, we need only the assembly language, not the C language, for storing and returning purposes. So assembly language to store registers not from the process that was interrupted by the timer, but to use registers from any process which need. That is the main concept. It is going to the assembly language is used by all the processes or all the tasks. The set of registers that define a process is known as context, and switching from one processor's register set to another is known as context switching. Okay, maybe the A register, it may be used by one process. B register, it may be used by the other process. Now from switching from one process to register processes registers set to another is known as context switching. The subroutine 1, imagine that you have subroutine 1 and subroutine 2, two tasks, task 1 and task 2. Maybe the subroutine, it may be having using the register B, and subroutine 2, it may be using the register C. Okay, so now the subroutine 2, it may request some data from the subroutine 1. That means it is going to use the register B. Okay, so this kind of utilizing the other subroutines register is simply called as context switching. The set of registers that define a process is known as context. Okay, that means the set of registers where the task is saved, and switching from one process register set to another, okay, when it is needed, is called as context switching. The data structure that holds the state of the process is known as record. Okay. So the next thing is the process priorities under preemptive scheduling. So how does the kernel determines what process should be run at the next moment? So you know the kernel is the part of the operating system that makes the decision to submit the CPU to either of the task, right? So how, in what kind of measurement the kernel is switching the task? We want a mechanism that executes quickly so that we don't spend all our time in the kernel and starve our process that do the useful work. If we assign each task a numerical property, then the kernel can simply look at the processes and their priorities, see which one actually to execute or to wait for waiting a data, and select the highest priority process that is ready to run. Okay, this mechanism is both flexible and fast. So like kernel, it is using task 1 and task 2, and the priority is given to any of the task at a particular moment. So like what the idea behind the process priority is, before uh, doing the kernel process, we can start prioritizing the task. Okay, and then let's do the OS, operating system, sharing the CPU thing. So what happens if task 2 is given higher priority initially by the programmer? Only the task 2 will be running at the first moment or instant of time. Okay, not kernel is sharing the CPU for both system, even though the priority is given like in the middle of the operation. It is not going to be quite worthy. So first let's assume, or let's fix the priority. Highest priority should be running at the first moment, and after finishing the highest priority, the lower priority will be following. Okay, so this mechanism is going to be both flexible as well as fast also. Okay, so let us see about the priority based scheduling. Okay, so you all know the CPU is the scarcest resource, and sharing the CPU by 2 or 3 tasks, it is going to be very challenging thing. So that firstly we have to make some priority before sharing the CPU. Okay, so this priority can be made by keeping in our mind regarding the performance requirements and the speed, everything. Okay, so before you prioritize a particular task or you schedule something, the performance requirements and speed, those things should be put in mind. Okay, one of the type of priority based scheduling is round robin scheduling. Okay, a common scheduling algorithm in general purpose operating system is called as round robin scheduling algorithm. So all the processes are kept on a list. Okay, whatever the processes, they are kept on a list or a database and scheduled one after another. This is generally combined with preemption so that one process does not grab all the CPU at the time. So you know the concept of preemption. Preemption, it uses the kernel, right? So that all the processes or all the tasks can be utilized by means of the CPU, so that we can avoid one process sharing the CPU at all the times. Okay, so this round robin scheduling algorithm will keep all the processes list and schedule one after another. So round robin scheduling provides a form of fairness in all the processes getting a chance to execute. So that is one of the advantage of round robin scheduling algorithm. However, it does not guarantee the completion time of any task. As the number of processes increases, the response time for all the processes increases also. Okay, so the real-time systems in contracts requires the notation of fairness to include timeliness and satisfaction of the deadlines. So process priorities, let's see about the process priorities. A common way to choose the next scheduling process in an RTOS, real-time operating system, is based upon the process priorities. Okay, so here also the main thing they are going to implement is about the process priorities only. So each process is assigned a priority and an integer value number. The next process to be chosen to execute is the process in the set of ready processes that has the highest value priority. So what they are coming to say is like each process is given an integer value number. Okay, so based upon the integer value number, the higher priority task is first executed. Okay, so this is explained by means of an example. Let's see the example. Example of an priority driven scheduling algorithm is given here. Let's define a simple system with three processes as seen below. So we have taken three processes or tasks. Let us consider the processes to be P1, P2 as well as P3. Okay, so and they have given the priority also. P1 is given the first priority, P2 is given as the second priority, and P3 is given as the third priority. And the execution time for the P1 is 10, and P2 is 30, and P3 is 20. So each process has a fixed priority that does not vary during the course of execution. So it is fixed. There is no more change in the prioritization. So more sophisticated scheduling systems do in fact change the priorities of the process to control what happens next. But we are not going to discuss that kind of change. Here the priority is at most fixed priority. So the ready process with the highest priority, with 1 as the highest priority of all, is selected for the execution. So as I said before, they are fixing an integer value. So if the integer value is fixed as 1, it is scheduled as an higher priority. Okay, a process continues execution until it completes or it's preempted by a higher priority process. So even it can be preempted by an higher priority process, or this process is going to continue until the execution process is completed within 10 millisecond or the duration of the time. Okay, execution of time. So therefore, from the previous tabulation, we can understand that already the priorities is being scheduled, and we know that P1 is always given the first priority. The integer value is set only for the first process P1. Okay, so now when the time of P2 is executing, okay, or it is ready to execute, during at that instant P1 becomes ready. Okay, and the time of execution, the time is going to be 15. Okay, and the 15th time is given to, the process of execution for P1 is only 10. Okay, so after 10 it is given to the P2, right? So now at the time of 15, P2 is ready to execute, but at that time P1 becomes ready. So what happens? Automatically you know that P1 is being given the highest priority. That means it preemits the P2 and begins execution because it has the highest priority. So instead of P2, P1 is executing. Okay, at the same time, when P1 is executing, P3 data is also arriving at the time 18. But do you think that P3 is going to execute now? No. It has to wait until P1 task is completed, and then also it should wait. The P3, the process P3 should be wait until the P2 task is completed. After that, only after completing P1 as well as P2, only P3 can be executed. Okay, so this kind of algorithm is called as priority based algorithm. Okay, so also in addition to the describing properties, we assume that P2 is ready to run when the system is started, but P1 data is arriving at 15 and P3 data is arriving at 18. But what happens as soon as this P2, in between the P2, as well as it is ready, P1 should be executed and then followed by the P2 and then P3 should process. Okay, this kind of execution is called as round robin scheduling algorithm. So the next topic is about inter-process communication. Okay, so what do you mean by inter-process communication, IPC? It is a set of programming interfaces that allows the programmer to coordinate activities among different program processes that can run concurrently in an operating system. Okay, so it is a set of interface that allows the programmer to coordinate the different activities that can concurrently run in an operating system. Okay, this allows the program to handle many users' requests at the same time. So it can be discussed under shared memory and message passing. You can see the figure, we have the shared memory communication. So here we are using a CPU as well as the IO device. So CPU and IO device, they both are sharing the same memory space. Okay, so what happens, like what do you mean by IO device? Input and output device. Those things are called as peripheral devices, right? Now the CPU and the IO device, they both are connected to the memory device by means of the bus. Okay, and also the CPU, it is going to write some details to the memory. Okay, and when the IO device needs something to read from the CPU, it is not going to directly communicate with the CPU, but instead it is going to communicate with the shared memory location. Okay, so whatever the CPU writes to the memory is shared to the IO device. That means the IO device is going to read the data from the shared memory location. So for all these things, we need the system bus also. Okay, so there are two components such as CPU as well as IO device communicate through a shared memory location, right? The software on the CPU has been designed to know the address of the shared memory location. Okay, the shared location has also been loaded into the proper register of the IO device. Okay, it is going to share the register also. Okay, the CPU wants to send the data to the IO device, so it writes to the shared location. Okay, the IO device in turns reads the data from the shared location. The read and write operations are standard and can be encapsulated in the procedural interface. So all these data are a standard thing and can be encapsulated in the procedural interface. The input data arrive at the constant rate and are easy to manage. The number of bits in the buffer changes constantly, and compression and transmission process need additional size information. Okay, so whenever the CPU writes something to the memory, it is compressing and writing, and compression is one of the main important component for the data to be sent over to the reception side. Okay, the input data arrive at constant rate and are easy to manage. Okay, the CPU and the output UART shared a memory, and the CPU writes compressed character into the buffer, and UART removes them to fill the serial lines. Okay, so what kind of transmission they are using is universal asynchronous receiver transmission. Component is used between the CPU and the memory, and the memory and the IO device. So at the end of each process, at the transmission and the reception phase, a buffer is given. Okay, so the buffer is the temporary storage device which stores the compressed data. Okay, after that the compressed data is been expanded to either one of the section. It may be given to the CPU or it may be given to the IO devices. Okay, so once the data is returned to the shared location, it is being shared to the IO device. The IO device will start reading the same data from the shared location. So for doing all this communication, we need a bus and also UART device, universal asynchronous receiver transmitter device. So at each end of the transmission, there will be a buffer. The buffer stores the compressed data. It is a temporary storage device. Okay. After that, the data are being expanded and it is served to the particular area. So the next concept is about message passing. Okay. So message passing also, it comes under inter-process communication. Okay. So the message is not stored on the communication link, but rather at the sender's receiver at the endpoints. Okay, it is also like a buffer. Okay, okay. So this shared memory communication can be used as a memory block to just pass the message as an information, in which all the data are stored in the communication link or the memory. Okay, so you can see we are using two processors, CPU1 as well as CPU2. So the messages are being transmitted from CPU1 to CPU2 in by means of using the temporary buffers. It can also be an example for an home automated system, home control system, for just sharing an 8-bit of memory message, 8-bit of message. It can be used. It is only used for passing the memory, and it does not accumulates a lot of space. So I have prepared the revision questions for you. Okay, it starts from the beginning of unit 4, from the multitasking until the message passing, that is inter-process communication. So all the questions are here. They are very important, and you can start preparing this for your exams also. Thank you. Stay safe and be healthy.